Hello everyone, my name is CJ, and this video is going to be about my final project for my computational fluid dynamics class. So the specific project that I've undertaken is a benchmark case known as flow around the Ahmed body. This was first devised in 1984 by these authors, the first of which is S.R. Ahmed. And this is designed to be an approximation to an automobile's shape. So let's see what that looks like. So here we are. I've just rendered a 3D file of the Ahmed body here. And yeah, this is what it looks like. So I'll quickly rotate it just so we can get a good view of all the sides and the bottom. And believe it or not, this is actually the front, and that's the back. So the main features of this body are this rounded off front region. You have the slanted rear, and then you have the four sort of pegs, which I suppose would correspond to the wheels of an automobile. So how exactly do I intend to simulate airflow around this? Let's find out. So I'll be using the CFD software OpenFoam, to be more specific, the pimple foam solver, which is designed for transient incompressible fluid simulations. There are a lot of tutorials out there with sort of off-the-shelf solutions, but for this project I really wanted to design it from scratch and really develop a better understanding for things like the meshing. So we'll see how that ended up going. This table here is from the SimFlow Ahmed body validation case, and my boundary conditions and initial conditions will reflect this exactly. I use all the same conditions and values. I'm not going to go through every single one for the sake of time, but feel free to pause if you're more interested in exactly what I'm using. Alright, so here we are in ParaView, and we're looking at a wireframe of the mesh that I have set up. The mesh that I set up operates in 4 steps. First, we have the base rectilinear grid that you can see all around the body. And this is created, basically with block mesh, which is the OpenFoam's very basic meshing tool. Then I use Snappy Hex Mesh, and I define local refinement regions around the body. So it's not easy to see from this view, so let's maybe switch to that. Nope. There we go. Yeah. So you can see from the top the local refinement regions. There's one there, and there's one more slightly inside of it. Again, not the easiest to see, but there are 2 refinement regions with that strategy. Then, in addition to that, I have set it to automatically refine the grid even further, super close to the body. I believe this is called like surface refinement. And that goes up to mesh refinement level 6. So you got 0, 1, 2, and then it gradually goes up to level 6 near the surface. And then on top of that, this may be very hard to see, but we are able to get boundary layers, as a matter of fact. And I have set it so that we can resolve up to 5 layers. That isn't necessarily true for the whole surface, just wherever the meshing sees fit. So, results. Here I have plotted the drag coefficient and the lift coefficient that's been measured over the course of the simulation in time, and I've compared them to the experimental values, which are the orange dashed lines. And you can see that while the drag coefficient seems to be self-consistent, it is not consistent with the experimental values as much as I would like it to be. This is a 44% error. That being said, the lift coefficient looks way better. Both of these lines are almost on top of each other, and the error looks to be very small, in the order of a few percentage points. Here we can see on the top my velocity profile. Specifically, we're looking at the UX component. And this is over the mid-plane, so the y=0 plane of the simulation. And we can see my data on the top, and we can see some of the experimental and validation simulation data below. And while I'm not able to plot these the velocity contours the same way they have, we can see that the trends are very similar, right? We have the free stream value that decreases as you get closer to the top of the slant. We have again the free stream value that decreases as you go into that close wake region. And we can see that decrease getting lower and lower the same way that these dips are getting lower and lower. So this is very consistent with the validation data, at least in this respect. For the exploration part of the study, I'm going to be modifying the turbulent kinetic energy K, assuming a constant eddy viscosity in UT. As you can see in this equation, modifying K and keeping T constant means I have to modify omega in proportion to K. So I ran two cases, one with K and omega multiplied by 10 and one with K and omega divided by 10. Here we see the results of the parameter variation. On the top we have K and omega multiplied by 10, and on the bottom we have them both divided by 10. We see the results don't appear to change too much. The drag force is still around that 40 to 45% level. Percent error, and the lift coefficient is very well constrained in both cases. I would like to firstly thank Professor Cheryl Grace for teaching the class. It was very instructive and I learned a lot. I'd also like to thank my classmates for just being by my side in all of this, and of course, thank you for watching.